Welcome back to the AI Research Roundup. I am your host, Alex. Alright, today we're diving into a paper from the trending list called RoboTwin, Dual-Arm Robot Benchmark with Generative Digital Twins. The core problem it tackles is a big one in robotics, the lack of diverse, high-quality data to train robots for complex, two-arm tasks. To solve this, the researchers created a framework that generates what they call digital twins. From just a single 2D image, it creates a realistic, interactive 3D model of an object. It then uses large language models to generate precise robot movement code, creating a huge, varied dataset for training. The results are pretty staggering. Robots trained on this data saw success rates jump by over 70% for single-arm tasks and over 40% for dual-arm tasks. And for those of you who want to try this out yourselves, the authors have released the entire RoboTwin simulation platform on GitHub. It includes data collection scripts, task configurations, and the baseline policies they use for comparison, like diffusion policy and RDT. A policy, by the way, is the strategy the robot uses to decide its next move based on what it sees. So this figure gives us a great visual of the whole RoboTwin framework. It all starts with real-world data collection on the left. You can see it capturing both regular and depth images of a task. Then, the core of the system takes over. A foundation model, which is a large AI model trained on broad data, takes an image and generates a full 3D model. It even adds important spatial annotations, like the colored axes you see on the dustpan and brush. An LLM then uses these annotated models to generate robot code, creating thousands of expert demonstrations in a simulator. This whole process creates that generative digital twin. Alright, and this next figure really zooms in on that process, using a hammer as an example. From just one 2D photo, it generates the full 3D model. You can see its geometry, its wireframe, which is like the object's skeleton, and other data for physics. Then, crucially, it adds those important spatial annotations. You can see the points for contact for gripping, and a function axis showing the direction of the swing. The LLM uses all of this to break the task down, infer the rules, and calculate the exact robot pose that's its position and orientation needed to actually use the hammer. So we just saw how this works for the hammer, and this figure really drives home how versatile the system is. It shows the same kind of spatial annotations, those key points and principal axes applied to a whole range of objects. You can see a drill, a knife, a mug, and even a shoe. For each one, the system defines things like a function point, which is where the main action of the tool happens, and an approach axis, showing the best direction for the robot to come from. This consistent, geometry-aware labeling is what lets the LLM understand how to use completely different items. Okay, so now that we see how RoboTwin applies these smart labels to all sorts of tools, the big question is, can the LLM actually use this information to create successful robot plans? And this chart gives us the answer. It shows the success rate of the code generated purely by the LLM for the different benchmark tasks. The system uses a trajectory optimization library, which is a tool that calculates the best, most efficient path for the robot's arm to ensure the movements are smooth and collision-free. As a result, for many tasks like cabinet storage and block handover, the success rate is really high, over 80%. But it also shows where the challenges are. For instance, container place is much harder with a rate around 30%. And to collect that initial real-world data, and to ultimately test the final robot policies, the researchers use this physical hardware platform. This is the open-source Cobot Magic Robot. It's designed for teleoperation, which is where a human operator controls the robot remotely, almost like a puppet to record expert demonstrations. You can see it has 4 Agilex arms in total, 2 master arms for the human to guide, and 2 puppet arms that perform the task. It's also equipped with 4 Intel D435 cameras to capture everything from multiple angles. Alright, so we've seen the hardware used to collect those real-world demonstrations. This next chart really highlights the huge benefit of adding RoboTwin's simulated data into the mix. It compares success rates for 2 tasks, bottle pick and cup place. The solid lines show the performance when you train a policy, which is the robot's decision-making strategy, using only real-world data. As you add more examples, the success rate slowly climbs. But the dashed lines show the performance with 300 simulated demonstrations plus just 20 real ones. That combination provides a massive head start, achieving a success rate that would otherwise require hundreds of real demonstrations. And that performance boost isn't just for simple picking tasks. This figure gives a great visual overview of the different kinds of challenges included in the RoboTwin benchmark. You can see everything from single-arm actions, like hanging a mug or putting an apple in a cabinet, to much more complex dual-arm coordination. For instance, there's the dual shoes place task where both arms have to work together in a tight space, and block handover, where one arm passes an object to the other. This diversity is what makes the benchmark so challenging and useful for testing new algorithms. From simple placements to complex handovers, the RoboTwin benchmark really pushes the boundaries of what we can test. Ultimately, this work shows us a powerful path forward for robotics. By creating these high-fidelity digital twins, researchers can generate massive, diverse training datasets, which drastically cuts down on the need for costly and time-consuming real-world data collection. This could be a key step in making robot learning more accessible and scalable. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.